this. So I'm going to work with this expression that shorthanded written in the form of a power series, and to decompose it when n is 0, we have 0 factorial in denominator, which is 1, so no derivative, just the x minus something to the power of 0, which is 1. So there is no power of x, so just first term. And then for the next term is a first derivative. For the next is a second derivative. For next is third. And for the nth term will be nth derivative. And they all divided by corresponding n factorial. So the first term is divided by 0 factorial, then a 0 term. And first term is by 1 factorial, which is just 1, and then by 2 factorial, and so forth by n factorial. So they use this formula to decompose any function that should be differentiable, of course, into the power series with respect to that function. And then they see when it is convergent and otherwise. So function f of x, we're going to try to decompose into the infinite series. And of course, a function could be infinitely differentiable, that'd be very nice. So they take various functions. For example, if you take cosine of x and start to do this process of finding various derivatives. So if you take the derivative, I'm going to write x, I just put derivative f prime for the cosine, which is negative sine, right, of x. And then we have back to the cosine, but if you take another derivative, if you take second derivative, f double prime, then it will be a derivative of sine is cosine, but the minus sign will stay. And so Alex, I'm gonna do this for a long time. Well, that's actually 2 more steps, because not because I have difficulty writing on this computer, but because it's actually gonna stop in the cycle. So if you take the third derivative, it is gonna be a derivative of cosine, again, negative sine, but that will be a positive sine, right? So derivative of cosine is gonna be negative sine, right? And then there is another minus, so it's plus sign. Okay. And then finally, fourth derivative, you can put either a Roman numeral or like f index 4, or you can use 4 primes. So derivative of sine is cosine. So I ended up again with the same function we started with a function cosine, which means that if I keep going, they will repeat. So then, depending what point C they like to use, so let's say if you use the decomposition at, and now here's the example they consider. So if you look at the function sine, and then you try to decompose it around 0. So if I also do this around 0, but now as a function cosine, So what will be coefficients? I want to decompose it just like they did here in the example with the variety of powers. And well, looks like now I need to get those plugged into any particular number. So third derivative at 0. And finally, last, the fourth derivative will be the same exact as a function f of 0, right? So when I decompose in the neighborhood of 0, the powers are going to be x minus 0 or just powers of x, like first, second, so forth. So cosine of 0 is equal to what? 1, remember? Sine function. And then starts alternating 0, then -1, then again 0, and then again +1. So that'd be the same as fourth derivative. Excuse me, fourth derivative. So that's why we don't need to continue, because we can see the coefficients will start to repeat, but with one little extra, with denominators, right? So if I try to add these terms, so if I start to add f of 0, which is going to be 1, then if I go next, which is going to be derivative at point 0, which is 0, so one can say this is going to disappear. Okay, then next will be the second derivative, which is going to be -1, right? And then denominator is going to be factorial. I say, Alex, why is it factorial? Well, because of the formula, which is multiplied by x squared, the formula which is given to us, and that's the one I try to show you. So the next term will be 0, and the next is, again, the formula says the derivative at 0 divided by 2 factorial. So this is the formula in general that we have. Here's nice in denominator, which is actually 1 factorial, then x is 2 factorial, and x is 3 factorial, so forth. We get n factorial under the n's derivative. So that's the reason why this is looking like that. So let me return back to where it was. So notice that every other term here is going to be a 0, right? So these pieces are going to disappear. Okay. So every second piece will disappear. So what's gonna actually stay? Well, looks like the function cosine, where is it again? Cosine of x is gonna be turned into the following. So the first term is gonna be at point 1, which is 1, right? So where it's our coefficient 1 over 1 factorial times x to the power of 0, which is also 1. The next term will disappear because the coefficient is 0. The next term will be with a minus sign, so that'd be -1 over 2 factorial, or 1/2. you want, you can put 2 factorial so you can better see what's going on. And this is multiplied by x squared. And then next is again going to disappear, so I'm not going to write it. And then the sign changes. So we have a 4 factorial in denominator, and our power of x will be a very hard time to write things because this computer is different mouse, and I just have a hard time to write it. So x to the 4th. I have no idea what happened. I just worked everything perfectly yesterday, but today does not want to. So the next sign will be minus. So it looks like we have only even terms, only even powers of x. That's the point. So our power of x is now 6. So please notice these are sign alternating series with powers 2, 4, 6. I can say that's 0. So to be precise, you can say x0, 2, 4, 6, and then they alternate. So first power is gonna be well, looks like of x is 0, then 2, and so forth. So now with corresponding values of the power, we have a factorial. So how can I write this as a summation notation? Well, looks like it's going to be power of n, and since they're only even, it's going to be 2n. Look at that. And then the same exact factorial on the bottom, right? So it'd be the same exact number, 2n, but in your denominator. So that way you have only even terms, and that's good to realize, and make sure you put parentheses, of course. So these are our terms, and notice they start at 0. Excuse me, because the first term is going to be to infinity. The first term is 1. Right? So when you raise the power of 0, it's going to be 1. Now, the signs alternate, so there has to be a negative present or -1. And now what the power is? 2n? Not really, because power is 2n is going to be everything positive. We alternate, so I need to go from 1. So basically from raised to the power of n. So when first term is 0, -1 to the power of 0 is 1. So it is in this positive. But the next term has to have a minus sign, and when n is 1, the next term, indeed it's going to be minus. So I just produced the power series for decomposition of cosine. How about that? And all I used was the formula that we utilized for sine. Again, that's Maclaurin expression. And again, the point of story, you can produce decomposition for any function. It has to be just differentiable, and that's the goal. So this formula is very, very strong. Also, I noticed that so-called Maclaurin decomposition, that's around c equal to 0. So when you decompose around 0 point, what c could be 1, could be 2, could be any number, right? And well, usually we decompose around 0, but sometimes we utilized some other values, and the popular kind of decomposition is for binomial functions. So I have one here in one of the examples. And binomial series here. I think it's another popular case. And you already encountered the composition for binomial finite situations, such as, for example, if you work on x, let's say +1. And what if you decide to raise it to some finite power? Let's say power of 2. Well, we had a formula for that, right? So it's x plus 1 raised to the power of x plus 1. So it was a square of first, remember, plus 2 times multiplied by x and by 1, so it's 2x. And finally, plus the square of last term, which is going to be 1 squared, or just 1. But it's not really what we have here, but you can now look at the analogy. So you have 1 plus x, or x plus 1 raised to power of k. So if you use the whole power, well, then eventually you were to multiply this parentheses so many times with itself, or use so-called Pascal's triangle to produce those coefficients with those powers of x. But what if you have power like they have here, 1/3? What does that mean? Well, please notice if you have x plus 1 or 1 plus x, okay, all right, 1 plus x, raised to the power of 1/3, it's no longer going to be finite sum. The power is going to be actually the sum is going to be infinite, so that'd be a series, because when you start to take derivatives, notice they're not going to stop, they're not going to end. So let's say if you take it as your function, so don't copy it again. So if your function, let's say f, and if I take a derivative, f prime, 1/3 will be your now coefficient, right? The power rule for differentiating. But the actual power is now going to be negative. So it'd be 1 plus x in the parentheses, which is multiplied by power of minus 2/3, right? The rule of differentiation, subtract 1. And you can differentiate it again, and you can differentiate it again, and etc. You can differentiate it infinitely many times. You see, if you take, let's say, let me do one more, second derivative, then you're going to end up with that negative 2/3 that goes in front, so it'd be minus 1/3, and then that we used to have, right? And then you times it by 2/3. 2/3 now goes in front, and this parentheses, which is still same 1 plus x, we just copy it. It will be raised to the power of minus 1. So 2/3 with negative sign, subtract another 1. Would that be minus 5/3? So please notice the powers start to be larger negative. If you differentiate it again, you subtract another 1 or 3/3, so it'd be 8/3. And you can do it forever, and that's exactly what they're doing in here. So they use the formula, and powers of x are being utilized, and notice these coefficients that we produce at the with our values at the 1/3 will give you infinite series, and there'll be some coefficients here like 1 times 2 on the top and 2 times 3, which is gonna be here coming out, and then another 3, another so forth. So we get this whole story of infinite series, and that's a decomposition of power of 1/3. Remember, we never did that. We just stopped at 1 x plus 1 squared or cube, or maybe some of you saw x plus 1 to the power of 4. We usually don't go any further. But what to do with fractional powers? And turns out there are going to be infinitely many terms, dot, 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 using again decomposition that we discussed in this section. That's pretty interesting, right? So the point of story that from now on you can decompose pretty much any function. You don't care what it is as long as you can differentiate it, as long as people say smooth curve. And here's the bunch of decompositions that they provide us with here. So here's sine, here's cosine, and so forth. And you can see various popular functions this section is talking about. So it is a little bit tedious. That's something that we don't really want to continue. So they just stop and they end not just the section, but entire chapter, because this process can last you to do for a while. We look at the nicer functions, but there are all kinds of other functions as long as you can differentiate. And if there is a need, then you can do it. So the next section I wanted to discuss briefly, because that's something that you already learned back in your algebra classes. So let me clean the mess, and we have so-called second degree curves, conic sections. So I guess the picture here is very interesting. The way we can think of parabola now is a little bit different. So the parabola that we used to have, one was equation, something with squares, right? So y was on one side, and then x squared was on the other side. But what they do is they say x minus h squared on the right side and 1 minus k is on the left side. So they just had the vertex hk. That's very popular. Put equal sign here. Because now I started to produce mess. It's kind of hard for me to write on this computer, that's why. But it's not a good excuse. I had to take good care of my previous computer, but I'm not sure what's going on. So, anyways, where's the vertex? Well, the lowest point on the graph, right? Parabola HK. So that's something that I'm sure you know pretty well and wonder why I tell you all that. Well, they give a very interesting interpretation of this parabola. They say you can look at the conic section, which means to cut the cone here in such a way that your secant plane will be parallel to the side of the cone. And that way, what you produced in your cut will be parabola. So the parabola is produced if you cut with a plane parallel to the side. And if you're plane is not going to be parallel, then in a cut, there will be so-called ellipse. And if you're going to have a cut under some angle, so there will be two pieces. On the top and the bottom cones, then you produce hyperbola. And they're all going to have their centers called HK. And that's probably what you experienced when took intermediate algebra classes. That's where we discuss it in college algebra. So they show us this HK as a pair, the center of so-called vertex of the parabola. And now amazing fact about this parabola is that it has a focus. So each parabola has a focus, a special point in it, such that if you have a light and if you placed a lamp in the focus, then it's going to reflect through the surface of parabola. So if you made this parabola surface as a mirror, so it's going to be reflection. And no matter which beam of light you consider is going to reflect and go parallel with the previous. So you're going to get the ideal flashlight. So flashlight is made in such a way that here we have a parabola-like surface, then all the light beams, if the light is posted exactly at the focus, at that special point, the lights will go parallel, so it'll give you a good flashlight. That's the idea. So question is how to find focus, and here's the formula. It's 4p. So that's the something that they, I think, added. I don't think we talk about this in the intermediate algebra, but that's the idea. So there is a focus. And in the parabola, we have a focus as well as in ellipse, as well as in hyperbola. So all these special curves of second degree, because if you look at the equation of ellipse, for example, or ellipse, so you can see the equation, and it's analogous to parabola. It has square term for x also minus h and y minus k, and the key idea is to have one on the right side. With parabola, we don't have y term squared, but with ellipse, both an x and y squared. And there's a way to produce the graph of ellipse using focus point. Actually, it has two focus or foci, they call them. So they have the same string. So if you tied the string between those two foci, then if you keep rotating it, the sum of the distances to foci will be always the same and equal to the length of your string. So that's how it's produced in the picture of ellipse. We don't really get much into this story in our class, though, and we actually no longer get into this story because there was a class called Calculus 4 that they successfully canceled, and it talked in very detailed and formulas and everything about various curves of this kind. So here we're just left with a brief section, so there is not much I can do, just tell you, look at this. Here's an ellipse. If we have x squared and y squared with a plus sign, and if it's subtraction, then you get a hyperbola. Hyperbola, and that's the last thing you probably also saw hyperbolas. We work a lot with hyperbolas, like 1 over x function, right? Hyperbola. So hyperbolas are here. So notice they're the same exact equation, but instead of pluses, we put minuses. So that's really all it is. So what they do here is they start to, well, differentiate those. And I wanted to briefly look at the example too, because again, that's something we already did before and it's really going nowhere because we don't really work much with this part of story since it was successfully canceled. But we used to have this Calc 4 for a while, about 20 years ago or so. They had this a big deal. It's a Calculus 4 class, but not anymore. So makes it, I think, a little easier on people that don't really need it, they say. And they used to require it for engineers, but nowadays I think they don't really require it to take anybody. So anyways, so our length of chord. So they want to find, looks like in this particular example, the part of parabola on the level of focus. So they say, okay, call this one point and the other point, and how do we find the arc length? Remember, there was a special formula that was dealing with the square root from 1 plus square root derivative. So technically, we don't really have any new material here at all. That's why I want to be brief. But I recall what we already learned previously, and previously we had the formula for the arc length. If you remember, it was a derivative squared under the square root. So that's prime, that's derivative. So if they give you equation of some curve, then all you need is just take derivative, and derivative of this function x squared will give you 2x, and so differentiate that equation with respect to variable letter x. And of course, I'll keep y prime, so 4p. So they didn't tell us what p is, so some kind of constant. That's why it stays multiplied, and then y prime is here. So this enables me to actually see what y prime is, right? So what is y prime? Someplace, maybe white color, so better see. So y prime is going to be this 2x over 4p, right? So I just use the formula, plug things in, and see if we can integrate it, and I don't think it'd be that easy, so we'll stop at that stage and let you enjoy this yourself, if you'd want to. If you plan to do more stuff and working with various integrations, then you can do it. But the point of story is that the formula is being provided in the tables of integrals, so you just plug things in, because I guess not many people want to do integration by scratch because it leads to possible mistakes and not really bring you much fun. So if I square both sides of this now, Alex, why would you square both sides? Not because I feel like squaring, because this is the actual expression I need. So my goal is to put the whole thing into the square root. So we're gonna integrate. We'll see from where to where, but now we have a square root extracted from 1 plus that thing. See? So arc length formula that we saw when we just started this class. I know it's been a while, but since we started, but the point is they're just using the old knowledge and That's about it. So divided by 4p squared. Well, okay. So it looks like now you want to put dx, of course, with this, right? And see how your x will vary. And x will vary symmetrically with respect to the origin point, right? That's here. So from minus 2p to plus 2p. And instead of doing minus 2p and plus 2p, we can go half. So I take a half and then double, and then from 0 to plus 2p. So that way I will first of all use my favorite number 0. So when I take antiderivative and then use fundamental theorem of calculus to actually put in the numbers, it'd be very convenient to use 0, because when we plug in 0, then everything becomes 0. So that's why it's advisable to always use integration with respect to 0 whenever the picture is symmetric, and then go twice. So not just that half and that half, but just get a half and then double. And that's how you get the whole thing. But now I need to take the antiderivative, so they do this, I guess, same thing I just did, right? But then when they get to the point where they need to take the antiderivative, notice they square root, all they done is they square root 4p squared, so they get 2p in denominator. So 2 is in front, and 2p and 2 will cancel. So you end up with this. Just p will come out. But then they do the trick. They say use theorem. And what theorem? We didn't have a theorem. They just use tables for antiderivatives. So they assume that this one is same as that. So technically, you could have replaced with the 1 plus tangent squared, right? So 1 plus tangent squared is secant squared. So you can square root secant squared, you get secant, and that way you can find antiderivative. But they say just use theorem. That's why I don't feel like continuing. You look at the theorem, it just gives you the ready answer. So you plug it in and you get the answer. It just spits out at you some kind of expression that looks nasty as that one. See, it's just, I would say, leads us nowhere. And I think at this stage, I'd rather just stop for today. And we have a final exam that's coming, right? The final, because next week is a week of finals. So I think I'll still can lecture a little bit, and I will email you the final, so you will be taking the final. Of course, I will say a few words next time about the final, and I will send it to you by email. And just like with a midterm, you have the whole week to take it, so I'm not gonna interfere, so you can take the final exam and email at your convenience. And I'm sure you're gonna get nice grade, right? Because you will have as much time as you need. Of course, if you don't wait for a month or something, because next week is week of finals, so I hope to get it sometime by Tuesday or something. So I will work on creating the finals so that it doesn't touch the new stuff, so it will be just coming from previous sections, and I will send it to you and I will tell you exactly what sections these problems that I created will be coming from. So I'll create two problems. I'm thinking about L'Hopital's rule, and the other will be something with conversions of series. What else can I ask? We worked with series, right? Various infinite series up to now, and then we also did some L'Hopital's rule. I think that's very useful procedure as well. So those two things. So I will ask you two exercises, as well as to email me your homework. Homework is another thing. So like from today's lecture, just do one exercise, just copy one, and that'd be good enough. And from previous lecture, you can just see a recording, right? And we you actually receiving the recordings from me every day after we end the lecture. I get that Zoom recording of the lecture emailed to you. I hope you keep track of it. It's the same thing you did for the midterm. Just copy one problem from each recording. Was not going to be very hard, but make sure that you do that and make pictures and email it back to me at your convenience. So over weekend, if you can do it, that we just. So homework that you should email one thing and the other is midterm. So I think it'd be a good idea that you start to put homeworks together. So I'm not asking you for this section. So this section will keep working with the chapter 11 next time. So we'll keep doing it and you don't need to worry about that for turning in. So I guess that'd be just for fun. But turn me in the stuff we covered since the midterm, right? So it's a little bit of chapter 11, chapter 10. That's what we need. So I guess at this stage, I'm gonna stop for today. So I'll let you go ahead and start to put those homeworks together. If you already have everything, just make pictures and email it to me. You can even do it tonight, anytime that works for you. Or if you did not do anything at all, good, you refresh your memories now, you relax, so now you're ready to push it hard, right? So over the weekend, copy those homeworks and email it to me. And next time we'll discuss in more details our final. All right, so that's the plan. I'm gonna stop recording. See if you feel like leaving, then you can leave. If you have questions, please ask me.